This is the intro video for AP Calculus BC, section 4.2, and in this video we're going to be looking at approximations of areas between the x-axis and a curve. So we're going to look at several of these. The first one is what we call a left sum. And left sum uses rectangles whose height is determined by the left side of each particular interval. So if you look at the picture here, I think it's fairly accurate. You can see that for this first rectangle, the height is determined not by the right edge of the interval, but by the height of the curve on the left edge of the interval. So we'd be using that left edge to determine the height right here. Oops, right here. There we go. And you can see that that pattern continues on as we move across. Every single time it's a left edge that tells, it's the left edge of the interval that tells the rectangle how tall to be. So if we were going to use a left sum to approximate the area, we would take all those rectangular areas and we would add them up, or sum them up to get the approximation. So how accurate is a left sum? Well, it really depends on one thing. Depends on, is the function increasing or decreasing or a mix of both. So if a function is increasing, we can see from the picture that a left sum would actually fall a little bit below the picture, a little bit below the curve. And so a left sum is going to be an underestimate on an increasing function. So put left sum on an increasing function means underestimate. Hopefully that makes sense. And then you can see that if we had a decreasing function, like kind of the right side of this graph, then it's going to be a very different result. So if we have a decreasing function, we use a left sum, then you can see all those rectangles are actually going to be above the curve. So a right sum on a decreasing graph will be an overestimate. So that's the main factor you want to consider, as to whether an estimate is going to be too high or too low. It's going to really depend on, is the function increasing or decreasing on that particular interval that you're looking at. Okay, next we'll look at a right sum. So as you can see, a right sum is very similar to a left sum, except the height of each rectangle is determined not by the left side, but by the right side of each interval. So you take all these rectangles, let's just focus on this one right here. You can see perhaps that the right edge of the interval is what tells the rectangle how high to be. Same thing over here. Right edge matches up with the curve. So the right edge of the interval tells the rectangles how high to be. Okay, so to estimate the area between the curve and the x-axis, we of course take all those rectangles and add them up, all the areas of the rectangles and add them up. So thoughts on accuracy. Again, this depends on increasing, decreasing, or a mix. So let's think about how this works with right sums. So if I have a function that is decreasing, and I use a right sum, and hopefully you can see that a right sum would be too low. It would be an underestimate. So a right sum on a decreasing function means underestimate. Of course, this will just be the exact opposite of what we saw with a left sum. So the alternative to this would be if you have a right sum on an increasing function. So a right sum on an increasing function would look something like that. And of course you can see that those rectangles are higher than the actual curve. So a right sum on an increasing function leads us to an overestimate. And if it were a mix, it'd be hard to tell. It'd be hard to tell exactly whether it was an over or an underestimate. Okay, our final one we're going to look at here is a midpoint sum. All right, with a midpoint sum, we do not use the height of the curve at the left edge or the right edge, but we use the height of the curve right in the middle of the interval. So it's a little bit harder to draw, but maybe you can see that this rectangular height corresponds not with the left or the right edge, but with right in the middle of the interval. Same thing here. That one's off a little bit, but hopefully you get the idea. That one's pretty good. You can see I'm using the height of the curve at the midpoint of the interval to determine the height of the rectangle. Again, not the left edge or the right edge, but the midpoint of the interval. Once again, to find the area, we are just going to sum up all the areas of those triangles. Accuracy, certainly going to be more accurate than the left or the right sum. Increasing, decreasing does not matter as in the same way. So let's just call this, at this point right here, the most accurate. Hard to determine whether it's too high or too low. It certainly would be the most accurate. As you can see, with really all of the rectangles, some of the rectangle is above the curve and some of it is below. Okay, so we're going to do one example here with this. And so all of these sums plus a few others are going to be soon known as Riemann sums, and we'll be looking at how to kind of formally look at those here soon. All right, so use a left sum and 6 rectangles to approximate the area of y equals 2x squared plus 5 on the interval from 1 to 7. So I'm going to graph this real quick. 2x squared plus 5, of course, is a parabola. And so I'm going to just, let's see here, 2x squared plus 5, we'll just do something like that. The interval, of course, it continues over here, but the interval is from 1 to 7, so I'll just do something like that. Okay, so it says use a left sum. So I'm going to sketch in at least a couple of these rectangles. So there is my first rectangle. And the first rectangle, well, actually, let's go back a little bit. How many rectangles can we even fit? Of course, we're supposed to be putting 6 in there. Made some nice, convenient numbers here for you. Of course, the distance between 1 and 7 is 6. So if you use 6 rectangles, the base length for all of these rectangles will be 1. So it'll be a nice, consistent base length. So I'm going to go ahead and say area equals, well, for the first rectangle, of course, the area is base times height, so it's going to be 1 times. And what we're going to do is we are going to use the height of the curve on the left edge of the interval. So that would be the height of the curve when x is 1. So when x is 1, the height of the curve is 7. Essentially, all that I'm really doing there is I'm plugging in a 1, which is my left edge, into my function. 2 times 1 squared plus 5 is 7. So that's the first rectangle. The second rectangle might look something like this. Again, we're using a left sum, so it'd go a little bit higher, but again, we're going to be using the left edge of the interval to determine the height. So once again, the base length is 1. That hasn't changed. But now we're not going to be using 1 to determine the height. We're actually going to be using x equals 2. So when x equals 2, the y value of the curve is 13. So that's the second rectangle. Let's do the third. So the third rectangle, once again, has a base length of 1. But this time we'll not be using 1 or 2 to determine the height. We'll be using 3, right? We're progressing across the picture each time we're adding 1. So if I plug in a 3, I get 23. So on and so forth until I have arrived at, of course, my 6 rectangles and finished at 7 there. So let's keep going. I'm going to go base length of 1. And there is my fourth rectangle. So this time I'm going to be using x equals 4 to determine the height. So that would be 37. We got 2 more to go here. So this time I'll be using x equals 5 to determine the height. Base length is still 1. If I use a 5 for x, it's going to be 55. And then finally, my final rectangle will squeeze in here barely, something like that. I'll be using a 6 to determine the height there. So 1 times, plug in a 6, what do we get, 77 I think? There we go. Okay, so to actually find the area using a left sum, I would then take all those numbers and add them up. Kind of an important note here, I think, If you were asked to use a left sum and you're going to be graded on it, you want to make sure that you've given evidence that you used a left sum. The best way to give evidence that you used a left sum really is to list something like this, where you're listing all the appropriate bases and heights multiplied together. If I were you, I would hesitate from just doing a lot of multiplying in my head. Of course, all the bases were 1 here, so that's not very difficult multiplication, of course, but that won't always be the case. We won't always have base lengths of 1. So you want to always give evidence, and of course we can add these up. You could use a calculator. Of course, we can do this without. Let's just double check here really quick. I've got 20, 43, 80, 135. I got 212. I think that's right. I'm sure you'll tell me if it's not. But in any case, that is an example of a left sum. When you come to class next time, we'll look at right sums and midpoint sums and a few others as well. See you next time in class.